I know what you're thinking. Gradient descent is the optimization method for finding the minima of functions and is the powerhouse behind machine learning and AI. But what is it optimizing? And why is it so frustratingly difficult to get machines to learn? This is how I think about gradient descent. Remember that trick you learned in school to find the minimum of a function? Well, most of the time, it doesn't work. This is one such function where if you took the derivative and set it equal to 0, you would likely get stuck trying to solve for x. So how can you find the minimum of a function if you can't simply use calculus? Forget everything you know. Finding the smallest value of a function would require evaluating it at all possible inputs and reporting the smallest observed output. In practice, however, you can't evaluate a function on all possible inputs. It would take forever, so you need to limit yourself to a finite range of values. The larger the range, the more of the function we can observe, but the more work it requires from our computers, and work makes our computers sad. At the end of the day, we will never be able to observe the entirety of the function. There will always be a chance that a smaller minimum exists outside our chosen window. We can't know ahead of time the location and size of the window that will contain the smallest value. Instead of randomly guessing, we can slide the window around to observe more of the function. By strategically choosing the direction in which to slide the window, we can find smaller values more intentionally. For example, if the current smallest value is, say, in the bottom right corner of the window, we can slide the window toward the bottom right in the hopes that the function will continue to decrease in that direction. If the smallest value is within the window, then great, we've found a minimum. This strategy works even if we reduce the size of the window, which requires evaluating the function at fewer values. That makes our computers happy. Does this strategy still work if we reduce the size of the window as much as possible, collapsing it to a single point? Intuitively, we might struggle to see how we could know where the function is decreasing if we only have a single point to work with. But recall that derivatives represent the instantaneous rate of change of a function. In multiple dimensions, we call the gradient the vector that is the combination of the rates of change in each of the coordinate directions. Since the gradient is the direction of the steepest rate of change, by following the direction opposite to the gradient, we should eventually end up at a minimum of the function should it exist. It's important to keep in mind that the point lives in the input space, which, in these examples, is the 2D plane below. So we're trying to find the minimum of a three-dimensional function, but we can only nudge the point in the 2D plane. Most lectures on gradient descent start with the analogy of getting lost hiking in the mountains, having to find your way back down following the direction of steepest descent. This is a misleading analogy because when you're hiking, you're moving in the 3D space that's supposed to be reserved for the function space and is distinct from the 2D input space the nudges are coming from. A more accurate but complex analogy would be one where you're walking beneath the mountain trying to control a projection of your body doing the actual hiking. You can see nothing of the mountain, only knowing which 2D direction has the steepest slope. Although this strategy may seem flawless and foolproof, it's actually riddled with caveats and strange behaviors because of how little of the function we can observe each step of the way. Notice that the success of this strategy deeply depends on where you start and how much of a nudge the point gets every step of the way. Nudge the point too little, you may never reach the minimum in a reasonable amount of time. Nudge the point too much, you may end up wandering the function space for eternity. Surprisingly, walking in the direction of steepest decrease can produce increasing function values if the step size is too big, which could lead us to overshoot a better minimum that was close by. Sometimes this works in our favor, and we can overshoot a worse minimum in favor of a better one. We can also end up getting stuck in a loop. Mathematically, taking a step in the direction opposite to the gradient requires subtracting the gradient evaluated at that point multiplied by a set step size. So while we can define a constant step size, the amount by which the point is nudged also depends on the size of the gradient at that point. The steeper the slope, the larger the gradient, the bigger the nudge. As the point approaches a minimum, the nudge gets smaller and smaller. Finding an appropriate step size then completely depends on the chosen starting point. And slight changes to that starting point can lead to drastically different results. I know what you're thinking. If this video ends without explaining how to avoid all of these pitfalls, but this might actually be the topic of my next video. I hope this helped you better understand gradient descent. Like and subscribe for more content like this.